Hi there, welcome back to INFR 2670. This is lecture 8. It's about high availability in general and in the cloud, of course. And so just as an introduction, any form of data center outage will will have an impact on business continuity and all the organizations that use their services, right? So those the data centers, they are designed to operate with increasingly higher levels of redundancy to sustain high availability. So those data centers, they usually have redundant uninterruptible power supplies, for example, cabling, environmental control subsystems that will anticipate system failure, and also communication links and clustered hardware for load balancing, and etc., etc. So first, let's take a look at some of the outages we've seen in the past, just to show you that these outages happen even to bigger, cloud and bigger IT providers. And then we move on to high availability and load balancers and other things. All right, so here we go. So let's take a look at some cloud outages that happened in the past. So this one, in April 2011, Amazon AWS failed. They had a problem with misrouted traffic on the EBS, Amazon Elastic Block Store, that caused the volumes to remirror. But then it became a remirroring storm because each of the EBS attempted to back itself up on an available machine. So there was this crazy storm, right? What was the result? The Virginia data center went offline for 4 days. And that's a long downtime. So another one more recent, 2018, AWS again goes offline. They had a problem in one of the data centers in Virginia. So they had this direct connect, which is they have servers that with dedicated connection between their services and client companies. What happened was Alexa went silent, Slack went down, and Capital One Bank, that has the one of the main client companies directly connected to AWS, stopped. T-Mobile Sidekicks also goes dark in 2009. He had a week-long outage impacting customers' smartphones. What happened? Customers could not access email, calendar info, personal data, and Microsoft could not recover. They forgot to make backups. Google Gmail also failed. So in March 2011, I don't know, no, it wasn't, it was more in the US. So 150 customers had no access to Gmail for 4 days. And they had a bug that impacted data copied across all Google data centers. Well, there's not much detail, but that's all we know. Obviously, it affected Google's corporate customers using Exchange migration service, and they recovered from that by restoring data from physical tape backups. Yeah. Now, this is interesting, a little bit different. So in November 2007, Rackspace data center went down. A truck drove into a power transformer. So, and that transformer powered all the cooling units used in the data center. So what happens when you have no cooling? Servers slowly started exceeding heat and began shutting down. Pretty ugly. So those cases are just to show you that even the bigger companies, they suffer from unexpected failures, right? So now this lecture is about high availability. Let's see what it is all about. So high availability HA systems, they are configured to provide nearly full-time availability. Not 100%, not full, but nearly full-time availability, okay? And it's typically done through redundant servers and redundant hardware and software. And it's also an attempt to avoid single point of failure. All right? And when a fail occurs, a failover process moves processing tasks to the backup component. And this is usually in a matter of milliseconds, all right? And the more transparent failover is to users, the higher the availability of the system. Now let's take a look at fault tolerance versus high availability. They are different concepts, all right? So fault-tolerant systems achieve 100% uptime. And these systems are designed to guarantee resource uptime and availability. All right? Now, high availability systems attempt to maximize resource uptime and availability, but they cannot guarantee 100% availability. That's the main difference. It's a more realistic goal for many cloud providers, actually, right? And uptime may approach 100% in some cases, but downtime is still acceptable and expected. Usually you have scheduled downtimes, right? So measuring high availability, we can classify systems and evaluate their expected availability by system type. Email and internet servers, for example, they require greater availability than the applications with smaller number of users. Some other systems, they require continuous 24 hours uptime. And you may have other systems that require uptime in specific time frames. For example, stock market or some e-commerce due to high season sales or anything like that. Now, availability measurement is basically the mean time to recover and the mean time between failures. You'll see how we can use these two metrics to calculate the probability of the system being available. Okay? So, like I was saying, it's possible to measure the probability that a system will be available at any instance in time using this following equation. Availability is the mean time between failures divided by the mean time between failures plus the mean time to repair or recover. All right. And basically the A is the probability of system availability at any instance in time, and it goes from 0 to 1. So before we go into how we can achieve high availability, I just want to also show you another measurement of availability that you see out there, which is the number of nines. Okay, just another metric generally used. In the example, we have 526 minutes of downtime per year, which is 99.9% availability. That means we have 3 nines availability. You will see that a lot in the literature. All right. 5 minutes of downtime, another example, you will have per year, you will have 99.999%, and that is 5 nines of availability. There's also 6 9 of availabilities, which is like the pinnacle of high availability. We'll discuss that in a moment. So, pardon me. Here are some examples of causes of unplanned downtime. So, system faults is one of them. Data and media errors, and site outages, right? Outages, natural disaster, power failure, sabotage, whatever. Data, and you can have human error or media error, like a disk failure, for example. And system, well, any system component may fail. CPU, memory, power supply, software may fail, right? Peripherals, power, network, anything can fail. And unplanned downtime is disruptive, right? And it's also difficult and sometimes impossible to predict. Now, in this example, in this diagram, I have some examples of planned downtime. They are generally classified as routine operations, periodic maintenance, and upgrades. They can be disruptive as well, but well, one example would be in global enterprises. They support users in different time zones. That could be disruptive. And high availability then considers all these causes of downtime in the design of solutions. So, how can we improve availability in regards to the given formula that we discussed? How can we improve availability? Well, one way of doing that is when we increase the mean time between failure, MTBF. We increase it to very large values, for example. Or we can reduce mean time to repair, MTTR. So you reduce to very low values, right? And then the resulting of this formula will be something close to 1, right? You cannot make this 0, meaning there will be no time to repair. I mean, it's always fixed, right? I mean, There is almost no way. Well, there is a way, but it's expensive, right? So high availability then is achieved by manipulating MTTR and MTBF when designing processes and systems to meet availability requirements. For example, 5 nines. All right. So how can we address MTBF to increase high availability? So here we have a graph that shows the MTBF bathtub curve. It is a, we call it bathtub. It looks like a bathtub, all right? And it represents the evolving life cycle of hardware failures within any computing system. So you can see here we have early infant mortality failure. You know, those systems that will fail in the beginning due to lack of testing, burn-in, right? And well, with time that tends to diminish, right? On the other hand, you have wear-out failures. They start very low and then they go up with time. Systems start to wear out. We have also we have to consider constant random failures. And well, it's a line, it's constant. And the observed failure rate then is the blue curve, which is what we call the bathtub. And you can see in the beginning you have a high failure rate. As you use this, the time goes, the systems get more stable, right? And then in the end of the life cycle they start to fail. So why am I showing you that? Well, because we can increase MTBF by addressing each aspect seen in this hardware failure lifetime graph. For example, high quality validation of design, heavy burn-in period, like testing, before going online. Use better components. Why not? Better quality, component redundancy, etc. Design systems to withstand random failures. How can we do that? Fail over. We'll discuss some of those features. Preemptively replace hardware. Obviously, at the end of the cycle there, you start to replace them before they fail, right? So there are ways to increase hardware MTBF. Now, how can we address MTTR, or time to repair, mean time to repair, to increase high availability? So the first solution designed to meet minimum high availability requirements for most important systems, at least, it's 99.9% or 3 nines of availability. How is that achieved? Well, you can have spare inventory held on site for quick repair or swap, right? You can have technicians dispatched when failures are detected. You can have code failover to another location if needed. One example, let's say you have an MTBF, the mean time between failures is 10,000 hours. And the time to repair is 4 hours. All right. So that'll give you, and this is 99.9, 3 nines. All right. that'll give you 40 minutes a month of downtime, or 8 hours and 46 minutes a year. So yeah, it's doable, right? 3 nines is okay. I mean, now 5 nines. So now we're talking about, enterprise level solutions designed to meet the minimum high availability requirements for, most mission critical systems. So we're talking about 5 nines uptime, right? How can we achieve that? Again, you can have spare inventory that is held preemptively on site for the quick repairs or swaps. You can even have software automatically recovers from failure through the use of something like a high availability framework. You can do hot failover to another data center if needed. Obviously, everything costs, right? You are increasing availability, you're increasing the costs as well. But let's say in this example, we have a time between failures of 10,000 hours, like the other example, but the time to repair is 1 minute, right? Then you achieve 0.4 minutes a month of downtime and less than 5 minutes a year. That's impressive, right? Now, achieving 6 nines of availability, it's the, like we say, the pinnacle solution designed to meet the HA requirements for the most mission critical systems in the world. And how can it be achieved, right? Well, now you can have services replicated to on-site spare hardware, right? You can also have the same software that automatically recovers from failure using the HA and replication frameworks, for example, hot failover. All right. Optimize recovery speed if you use this kind of hot failover. In the example, you have 10,000 hours of time between failures and 5 seconds of recover or repair. Then you achieve something like this: 0.04 minutes a month of downtime and half a minute a year of downtime. That's crazy, right? It's almost fault tolerant, which we'll discuss. What we just discussed, actually. So now let's talk about software automation to reduce MTTR. Every high availability system performs the following steps to meet the system's high availability requirements. So it's fault detection. Detect the fault. This is the first one. Fault isolation, right? So fault detection, fault isolation. Isolation removes and terminates the service from the system, and this is usually done by usually following a set of administrative policies. And then you have service recovery. When services are just restarted if needed, and recovery steps are escalated if restarting the service does not solve the issue. And last one would be notification. So admins and technicians, they should be notified about the failure. So these are the usual steps that the software automation will take to meet HA. Let's talk about failover now. So, failover for high availability usually requires accurate instance monitoring or heartbeat mechanisms, and the system in a failover, it must be able to quickly and accurately synchronize resources during failover. And synchronizing, or what we also call, you will hear a lot, remastering, it requires the graceful shutdown of the failing systems. It also requires accurate information about resources available, remote and local. And it also will make the information available to recovering instances. And it also provides redundancy, or uses redundancy and load balancing, which we'll discuss in a moment. So how do we provide redundancy? So traditionally, redundancy was provided at the hardware level. That means you would have redundant compute components like memory mirroring, multiple buses, etc., which are very expensive. Do you agree? It also means you have redundant storage, RAID, mirrors, hot swappable drives, SANs, etc., which doubles the storage costs, right? And you also need network redundancy, firewalls, load balancers, etc., to help reroute traffic, and dual network interfaces that may provide full failover. So, what are the 5 levels of redundancy? So 5 system aspects can be addressed in regards to improving redundancy. We'll discuss some of them in this lecture. Physical components, first one. Virtual resources, you have to take care of them. So far, like the traditional ones in the past, it would be mostly concerned with physical components, right? So virtual resources, availability zones, like all the cloud providers, they do, like Amazon, they have, different regions and availability zones. So regions and clouds. Like I was saying, older redundancy methods, they focus only on the underlying physical components that could fail in a system. And that means this does not account for things like virtual resource failures, software failures, or natural disasters, right? So ideally, we need to design for failure. What does that mean? So first, we need to allocate redundant virtual resources that can handle all the underlying infrastructure failure without impacting availability. Also, we can have isolation, allocation, and full failover that should be automated and optimized. Cascading failures, for example, shouldn't bring the system offline. And better redundancy also includes spreading virtualized resources across multiple availability zones. So these are all steps we need to take care when designing a system for failure. Okay, so each application component must be deployed across redundant cloud components, ideally with minimal or no common point of failure. And each application component must make no assumptions about the underlying infrastructure. It must be able to adapt to changes in the infrastructure without any downtime. And each application component should be partition tolerant. It should be able to survive network latency among the nodes that support that component. And automation tools must be in place to basically orchestrate application responses to failure or any other changes in the infrastructure. All right. And when designing for failure, you should assume everything will fail. All right. Let's take a look at some high availability examples. So in database high availability, this is one example. MySQL active standby replication model. It allows data from one server, the master, to be replicated to one or more slaves. So you have replicated data in your database. So just some examples of systems that use high availability like MySQL. So Redis, NoSQL also have a master-slave model that provides the same kind of real-time replication, replicating data to slave servers. All right. The Amazon Relational Database Service, RDS, it is a database as a service, DBaaS, okay, and it makes it easy to set up, operate, and scale any relational database in the cloud. RDS also makes it very easy to use replication to enhance availability and reliability for production workloads. And when we talk about mission critical workloads, they can be run with high availability and built-in automated failover from a primary database to a synchronously replicated secondary database in case that one fails. Another one is cloud storage, high availability. OpenStack Swift, it stores 3 replicas of all objects on different Swift nodes. Just another example, AWS S3 storage also has a guarantee of 3 nines. This is their downtime, 8.7 hours per year of downtime. Just now let's take a look at some load balancers also used in providing or helping high availability. But first of all, what is load balancing? What is a load balancer? It refers to efficiently distributing incoming traffic across a group of backend servers. For example, in server farm, server pool. All right. One example, if you have a high traffic website that serves hundreds of thousands, sometimes millions of concurrent requests from users, right? So in this example, in order to meet those high volumes, the best practice is basically adding more servers. So a load balancer, it sits in front of your servers and routes the client requests across all the servers. The servers that are obviously capable of fulfilling those requests I'd say in a manner that maximizes speed and capacity utilization. It also ensures no one server is overloaded. It distributes the load, basically. So these are the functions performed by a load balancer. So first one, distributes client requests or even network load efficiently across multiple servers. It ensures high availability and reliability by sending requests only to servers that are available. All right, and provides the flexibility to add or remove servers based on demand. Now, there are different load balancing algorithms. Why am I going to discuss them? Because when you use a load balancing algorithm, you can choose what kind of when you know, the best load balancers, they will support different algorithms, and you have to understand which ones to use. And you will have a lab around Nginx load balancer. So yeah, it's got most of those options. So the choice of load balancing method depends on your needs, of course, and round robin, for example, the requests are distributed across a group of servers sequentially. Okay? One server gets it, the other one, then it goes back to the first one. Well, I'll have a little diagram to describe them. So we have weighted round robin, which is like round robin, but it considers criteria like traffic handling capacity of a server, requests per second, for example. All right. You have the least connections algorithm as well. The new requests are sent to the server with the fewest concurrent connections to clients. So if you have two servers, one has more connections, current connections, the one with the fewer connections will get the request. And you also have IP hash. The IP of the client is used to determine which server receives the new request. I'll describe this in a moment. It's IP hash is useful when you want persistent sessions, for example. We'll discuss that in a moment. So round robin, like I said, it's very simple. You have your client there on the left side sending requests. You have your load balancer in front of your servers and, well, your services there. So you have service HTTP 1, 2, and 3, right? And the requests are coming. So the first, let's say request 1 comes. The server or service 1 will get it. Request 2 comes. The server 2 will get it. The request 3 comes. Service 3 gets it. And then request 4 comes. And then it goes back to your server 1, right? And so on. You see 5, and then 6 goes to the third one, 7 goes back to the first, 8 and 9 to the third one, right? So it's called round robin, sequentially. Now, weighted round robin, you have something here called weight, which, like I said, it could be a metric based on capacity, server capacity to handle requests, and any other thing. So you have your client there. It sends request 1. It went to service 1, right? And then 2, it goes to service 2, and then 3, it goes to service 3, and then 4, it goes to that one, because it's still under the capacity of that server, right? 5 goes to the other one. It is round robin, but then you will see when it changes. So 5, 6 goes to the third, and then a third. And then request number 7 comes, and this one has already 2, right? 1 and 4, so it doesn't get that request. The load balancer will send to this one, which has 2 only so far, so it gets 7. And then 8 is passed to this, and then the next one, since the other 2 they have already reached their capacity, request 9 is sent to service 3. All right, very simple. So this this is the least connection algorithm, and it's quite interesting and pretty simple to understand as well. You have your requests, and basically you have an active number of connections, and the load balancer will then distribute the incoming requests to a specific service which has the least number of connections. For example, a request comes, the first one, this service 3 should be the one getting the first one because it's got 0, right? And then it also gets, the other one has 15, the other one has 3, so it also gets 1, 2, 3, and then it's the same as this one, but, well, my diagram here isn't the correct one, but you got the idea. The difference here is that this one has a weight, and so number 3 is more capable of handling, that's why it gets more, so it gets 6 here. There is an equation, a formula to calculate which one that the load balancer uses to calculate which one will get based on weight and number of connections or transactions. All right, but you got the idea, right? And then when it gets to decide which one will receive the request, it looks into the number of connections. And in this case, it's also weighted, so there is another formula to calculate that. It's basically that. And this is our fourth algorithm, IP hash. So it's deterministic. The result will always be the same if there are no changes in the elements involved in the hash. A hash is applied to the source IP of the incoming request, and it takes into account number of servers and their weight. So the following events, they may change the hash. So if a server goes down, if a server goes up, if the server weight changes, but there is an issue with that, which is for each change, when a change happens, it can redirect everybody to a different server. Meaning you are in a session and then you are redirected to a different server. That can be an issue. So some load balancers, they implement a consistent hashing method for session persistency. So source IP hash load balancing, it uses an algorithm that takes the source and the destination IP address of the client and the server, and it uses them to generate a hash key. And this key is used to allocate the client to a particular server. All right. So as the key can be regenerated with if the session is broken, this method can ensure that the client is directed to the same server that it was using previously. So that's really cool. This is useful, right? And it's important that a client should connect to a session that is still active after a disconnection and reconnection. So session persistency, or it's basically when we're talking about information about a user session that is often stored locally in the browser, For example, you have a shopping cart application that, the items in a user's cart might be stored at the browser level until the user is ready to purchase those items, right? So in that case, changing which server receives requests from that client in the middle of the shopping session can cause performance issues or transaction failure, right? So in such cases, it's essential that all requests from a client are sent to the same server for the duration of the session. And basically this is known as session persistency or session persistence. And the best load balancers can handle session persistence as needed. And another example or use case for session persistence is when an upstream server stores information requested by a user in its cache to boost performance. So in that case, switching servers will cause that information to be fetched for the second time, causing performance and inefficiencies. Now, there are typically two types or flavors of load balancers: hardware-based and software-based. Okay, so hardware-based provides proprietary software and specialized processors, and then if traffic increases, you have to buy more or bigger machines from that same vendor. All right. Now, software-based run on commodity hardware, right? It's less expensive and much more flexible than hardware-based load balancers. And you can run them locally, you can run them on a cloud VM or in a container. Imagine you can use containers and spawn them automatically based on triggers, right? Now, load balancers in the cloud. So just summarizing and then applying that to the cloud, right? A load balancer is basically a piece of hardware or it could be a virtual hardware software, right? That acts like a reverse proxy to distribute network and or application traffic across different servers, right? A load balancer is also used to improve concurrent user capacity and the overall reliability of applications. A load balancer then helps to improve these by distributing the workload across multiple servers, decreasing the burden, the overall burden placed on each server, right? So in a cloud, you will have load balancers distributing the load between, availability zones, for example, which improves reliability, not only, performance in terms of performance, but also availability, reliability. Now, some examples of existing load balancers and how they apply to clouds, right? So, for example, some features provided by ELB, and the Amazon's Elastic Load Balancer. One of them is it distributes incoming traffic across EC2 instances in a single availability zone or multiple availability zones. ELB also auto-scales its request handling capacity in response to incoming application traffic, right? It also detects the health of instances and then it no longer routes traffic to unhealthy instances, for example. It also provides persistency, or sticky user sessions that can be bound to specific EC2 instances. You can think about this as cookies, right? And it supports SSL termination at the load balancer. Why is this important? SSL termination at the load balancer. Well, basically it alleviates web servers of that extra compute cycles needed to decrypt SSL traffic, and also the security risk of terminating at the load balancer is lower, is lessened when the load balancer is within the same data center and as the web server. Now, Nginx load balancer, it's used by high traffic services like Dropbox, Netflix, Zynga, etc. So this is the one we're going to use in the lab. Okay, so it is used by the majority of the 100,000 busiest websites. So you can see the market share of Nginx load balancer. It is software based, right? And it can be configured in all those round robin, wait robin, list connection, IP hash, all the algorithms you have, right? That's why I wanted to explain each one so you understand when you see the options there. So as I was saying, in the next lab, you will perform load balancing using Nginx. You will need 3 VMs, and then one will be your Nginx load balancer, and the other 2 will be web servers. All right, and then you will distribute the load among between the 2 web servers. That's pretty cool. Now, high availability with Docker Swarm. This is what I'm gonna do in the synchronous session. Okay, so don't miss that, because we're gonna have a hands-on activity for high availability using Docker Swarm. I'll just give you an introduction to that, and then we will revisit this and work on the activity. So Docker Swarm is basically a clustering and scheduling tool for Docker containers, right? And then you can obviously establish and manage a cluster of Docker nodes as a single virtual system. And this Docker engine, you will see there, the Docker engine is the layer between the OS and the container images. And the Swarm mode integrates the orchestration capabilities of Docker Swarm into the Docker engine version 1.12 and up. All right. So basically, you create a primary manager. You can have a primary manager and multiple replica instances in case the primary fails. Right, and you can deploy manager and worker nodes. We'll discuss them all. So you have manager and worker nodes in Docker Swarms. So you can deploy them in runtime. And then it distributes and spawn new nodes as traffic or demand increases. It's pretty cool. Also, it ensures containers are launched on systems with adequate resources, meaning, the Docker orchestration will do that for us while maintaining necessary performance levels. And you can also export ports for service to an external load balancer. You can use other external load balancers. It's very useful. And then there are three different strategies. There is what we call the spread. It's default based on the node's availability, CPU, RAM, and number of containers running. And you can also have bin-back, schedules container to fully use each node. And here, once a node is full, then it moves to the next one in the cluster. It uses less infrastructure, right? Because it uses the node to the fullest, but it also leaves more space for larger containers on unused machines, but we'll look into that later. And you have random, which is just, choose the nodes at random to run to get the requests. All right.